Hello and welcome back to Abstract Linear Algebra, the video course where we talk about general vector spaces and general linear maps. And in today's part 24, we will talk about so-called homomorphisms and isomorphisms. And I can already tell you, in linear algebra, these names just describe linear maps. But as always, before we start with the explicit definitions, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. As a supporter, you get access to all the video courses I have, and you just have to click the link in the description to find them. Okay, then let's immediately start, and we already know a linear map L acts between two vector spaces V and W. And indeed, the defining property for a linear map is that it preserves the structure of the vector space. And you know a vector space only has two operations, which means a linear map conserves the addition and the scalar multiplication. And here it's important to remember that in mathematics, every map that preserves a given structure is called a homomorphism. Hence, in the context of linear algebra, homomorphism and linear map are synonyms. However, if we want to be precise, we would say a linear map is a vector space homomorphism. And at this point I can already tell you, an isomorphism is just a homomorphism that works in both ways. This means, to understand that, we have to talk about invertible maps. And this is not so complicated because we already know what the composition of linear maps is. In particular, this means that we could compose L with another linear map K. And indeed, it's definitely possible that the codomain of K is V again. And we have already learned that the composition is again a linear map. So for K after L, we put V in and V comes out. And now if we ignore any additional structure here, we can talk about these maps on the set level. So let's consider a map F that sends V to W as well. But here we don't need the vector space structure, we just need sets V and W. And then the notion invertible makes sense for a map if we find another map G. And now, not so surprising, this G should map W to V. And it should just invert the action of F. This means G after F is the identity map. More precisely, the identity map on the set V. And moreover, we also have it the other way around, so we have F after G is also the identity map. However, there we start at W, so it's the identity map on W. So this is what we mean by an invertible map on the set level, and you already know this G here is uniquely determined. So if F is invertible, then there's only one map G. And usually then it's denoted by f to the power -1. And moreover, you should know that on this level, being invertible and being bijective is exactly the same thing. So you should remember, if we talk about maps on sets, we can say invertible or bijective, but we mean the same thing. However, now going back to the topic of linear algebra, we want to know what happens with the inverse map if we consider the property linear. And in fact, we get a very nice result in linear algebra, namely the inverse of a linear map is already linear. In other words, this preserving of the linear structure works in both ways. More concretely, this means if we take a linear map L from V to W, which is also bijective, which now we know means that we have an inverse map on the set level, then the conclusion is that this inverse map is also linear. So we see if a map conserves the linear structure, the vector space structure in one way, it also conserves it in the other way. And indeed, we have already explained this behavior in our linear algebra course. And the proof we have written down there also works in this general context because the only thing that goes in are the properties of a linear map. With that in mind, we can immediately look at a very general and important example. And this one we already know very well because it's about the so-called basis isomorphism. To make sense of this, we just need to take a finite dimensional abstract vector space V and a fixed basis B. This means we can say we have n elements in our basis. And now, as you might remember, we can simply send this abstract vector space to the concrete one Fn. And there we just take the standard basis given by the canonical unit vectors. And usually we denote them by E1, E2 and so on. And now we can just define our linear map phi b by sending each basis vector here to the corresponding canonical unit vector on the bottom level. More concretely, bj is sent to ej. And now what we get is a linear map, and we can also show it's a bijective map. To put it in other words, the opposite direction here also works. And now we know the inverse is also a linear map. So we have a linear map in both directions, and that is what we call an isomorphism. So you see, it makes sense to call phi b the basis isomorphism with respect to the basis b. However, now we can also write down the general concept of an isomorphism. So the only thing we need here is a homomorphism, which also acts as a homomorphism if we can invert it. So first, the inverse has to exist, and it also has to preserve the structure. So you see, isomorphism is just a homomorphism where we can go in both directions. So in particular, for our vector space structure, we only need a linear map that is bijective. Because then, as we have stated before, the linearity in the other direction is already given. So you see, this fact makes isomorphisms in linear algebra really easy. Also there, if there is confusion, we would just say we have a vector space isomorphism or just a linear isomorphism. Now for finite dimensional vector spaces, the example from above immediately applies an important fact for isomorphisms. It tells us if we have an isomorphism between v and w, then the dimensions of v and w are the same. Simply because we immediately see that the number of basis elements cannot change. Hence, as in the example above, an isomorphism gives us a translation between both vector spaces. So you could say both vector spaces are essentially the same. And we can always decode back and forth by using our isomorphism. And exactly this fact will give us the tool to describe linear maps as matrices again. And this is what I want to do in the next video, so I really hope we meet there again. So have a really nice day and bye bye.